So far we've been talking about natural log and e. So today we're taking a moment to talk about bases other than e and some applications. So this first part of the lesson, we're just doing a lot of reminders from 2-trig and pre-calc, just to kind of remember. We haven't done that in a while. So make sure you have your guided notes. That'll help it go quicker. All right, our definition of an exponential function to base a. Remember that a is any positive real number that's not 1, and x is any real number. So if that's the case, then I have a to the x is equal to e raised to the power ln of a times x. For example, 3 to the x is the same as e to the ln of 3 times x. Keep in mind that, remember we talked about those power rules last lesson. If I have two things in the power that are multiplied together, it's the same as having that second thing as another power. So if I have, for example, e to the ln of 3 times x, it's like that x is a power on the 3. So when the e and the ln cancel, you're left with just 3 to the x. Also keep in mind that a cannot be 1. Remember, if I have 1 to the x, that's always equal to 1, and that's just a constant function, not an exponential. We also have those rules for exponents. A to the 0, remember, is 1. We can add exponents together if they're the same base. Rule number 3 is what I was just talking about. If I have a to the x raised to the power y, that's the same as a to the xy power. All right, and here's a more visual way of seeing what I was telling you about. E to the ln 3 times x is the same as x raised to that power. So the e and the ln cancel, and then you just have 3 raised to the x power. All right, so just a kind of reminder there of how that works. All right, so our definition of a log of base a, and again, a is any positive real number, not 1. All right, so if I have log base a of x, that's the same as natural log of x over natural log of a. And this is just the change of base rule. So that's probably how you've seen it before, where you just do natural log of 9 divided by the natural log of 3. You may or may not have seen that now that our calculators just fill in those pieces, but hopefully you've seen change of base. And then again, think about why we need to restrict a. If a is 1, then I would have natural log of 1 in the denominator, and that would equal 0, and we can't divide by 0. So again, a cannot be 1. And then reminder of our rules, log of 1 is always 0, log of any base. And then we can expand by adding, expand by subtracting, or we can bring that exponent in front. This is that change of base rule I was talking about. Remember, I can use any base. I don't have to use natural log. But if I have log base a of b, I can do log of any base of b divided by log of any base of a. But we typically use natural log or log base 10 because those are ones we can do on our calculator. If you're not convinced or you've never seen that before, go ahead and try a few. So try that example, log base 3 of 9. Do that on your calculator, and then also do natural log of 9 divided by natural log of 3. And it'll convince you that those are the same. Yeah, that's what I was just saying. All right, so our properties, remember that y is equal to a to the x if and only if x equals log base a of y. This is how we change back and forth between exponential and logarithmic form. So for example, if I have 3 squared equals 9, which we know is true, that's the exponential form, then in logarithmic form that would look like log base 3. Remember, the base of the exponent is the same as the base of the log, and log base 3 of 9 is equal to 2. Log is an exponent, so that answer that you get of a log is always an exponent. So if you didn't realize that before, remember, log is always equal to an exponent. All right, so again, some of the same rules that we talked about with natural log and e, they apply with any base. A to the log base a of x is equal to x, and then vice versa, log base a of a to the x is simply x. So let's review let's do some examples, remind ourselves how to solve logs and exponential functions. So all we're going to do is change this from logarithmic form to exponential form. Oh, let me go back. We'll do this on the smartboard so I can write. Okay. Let me pull that up. All right, so log base b, where we're going to move that. This is the base, and this is the exponent. So I would have b raised to the third power equals 125. So take the cubed root, and we get b is equal to 5. All right, and then for example 2, again, if you want to try these on your own first, pause and then see how I do it, that's fine. Or you can just watch me do them. So we got to isolate the base first, so divide by 3. And that would leave us with 5 to the x minus 1 power is equal to 86 thirds. And then we're going to do the log base 5 on both sides. Remember, the log base 5 is going to be able to cancel with the base 5 in the exponent form. All right, so these are going to cancel, and I'm going to get x minus 1. Over here, I'm going to have log base 5 of 86 thirds. And then we just add the 1 over. So our x is equal to log base 5 of 86 thirds plus 1. That would be our exact answer. I believe if you put that into the calculator, you get about 3.0850. So again, you're welcome to use those yellow calculators just to do this simple math or your own. All right, so if we continue on, let's go back to our PowerPoint and talk about the derivatives. Okay, so again, we're going to have a as a positive real number, not 1. U is a differentiable function of x, so that's normal. U is just, can be anything besides x. Our derivative, let's look at part 1. Our derivative of a to the x is going to be equal to natural log of a times a to the x. So this looks very similar to e to the x, except we have that extra ln of a. And keep in mind, if I had e to the x, this would still apply. It's just ln of e is 1. So we wouldn't have to write that, and it would just be e to the x. Let me exit out here and kind of convince you why that is the derivative. So we're saying that the derivative of a to the x is equal to natural log of a times a to the x. Okay, so if I take a to the x, remember we said a to the x is the same as e to the ln of a to the x. So that's like I'm doing the same thing. Remember we said that was equivalent early on. And we also said that this was the same thing as if I pull down that x in front of the ln, that's like doing e to the x times ln of a. Okay, so if I do that, if I do the derivative of that, we know how to do, this is just an e to the x function. We know how to do the derivative of that. This is like e to the u. So this is like my u. All right, so I'm going to do e to the u, so e to the ln of a times my du. What's the derivative of x ln of a? Keep in mind, a is just a constant, so ln of a is also a constant, so that's just a constant times x. So the derivative of that is simply ln of a. So how does that equal that? Well, remember, this is the same thing as a to the x. So that's how we're getting a to the x times ln of a. And then the same would be applied to the a to the u. The same logic applies to that. The other thing I wanted to show you on number 3, your number 3, it says the derivative of log base a of x is equal to 1 over ln of a times x. All right, so again, it looks very similar to natural log of x. Remember, if I take the derivative of ln of x, it's simply 1 over x. All right, but that's because the base was e. Here, I don't have base e, I have base a. But if I had base e, it would be ln of e times x. ln of e is simply 1. But let me show you why. Okay, so again, if I do a little bit of replacement here, so what is log base a of x equivalent to? It's that change of base formula. Okay, another way of thinking that is it's just 1 over ln of a. Here, I'll write it here. That's the same thing as 1 over ln of a times ln of x. So if I'm taking the derivative of that, really the only part that has the variable is a natural log of x. So the derivative of natural log of x is 1 over x. This is simply a constant. Okay, so this is 1 over ln of a. So that's how we're getting our derivative of 1 over ln of a times 1 over x. All right, and then the same applies to, so getting back to our PowerPoint, that's where we're getting all of these rules for the derivatives of bases other than e. So now for integration, we're just going to be working backwards. Okay, so if I want to integrate a to the u, so look at your number 2 for right now. Look at the derivative of a to the u. Notice that it has natural log of a times a to the u. So if all I have in my integral is a to the u, the constant part that I'm missing is the natural log of a. So it's just like what we do in u substitution. It's like they multiplied by their natural log of a, which is just a constant, and then divided outside to compensate. So if I have the integral of a to the u, just that, then it's just going to be 1 over ln of a times a to the u plus c. Hopefully that makes sense to you. I don't know if you can read that or not. My strip at the bottom is kind of hiding it. It says, I will provide rules 2 and 4 and the integration on your test. That should be really great news for you. So these you don't have to memorize for at least this test. You'll have to eventually for your final in AP. But for this test, I will put those at the top. Okay, so you'll be good. All right, so now let's go back to some practice. Let's find the derivative. The derivative of 3 to the 2t over t. So this will be a nice quotient rule reminder. Remember, we have to square the function on the bottom. So our f prime of x, we're going to have t squared in the denominator. And then we start with that function in the bottom. We don't touch it for the first part. And then we're going to do the derivative of the numerator. So the derivative of the numerator, that's like a to the u. So remember, we keep that a to the u the same. So that's going to be 3 to the 2t. Then we have the ln of our base, so ln of 3. And then we have, since we have a u this time, the u is 2t. We have to do the derivative of that. So that's 2. So all of that stuff was just the derivative of 3 to the 2t power. All right, then we have subtraction. Now we're not going to touch the top function, 3 to the 2t, and we're going to multiply by the derivative of the bottom function, which is just 1. Okay, so let's simplify that a little bit. Notice that we have a 3 to the 2t in the numerator, so we can factor that out. And then that's going to leave me with 2t ln of 3, that's our first term, minus 1 all over t squared. Okay, so that's probably how you'll see it in the back of the book. All right, let's do this next one. So again, we have a product rule. So again, nice little review of product rule and quotient rule. So our first function is 5 to the negative x over 2. The second function is the sine of 2x. I'm going to start by doing the derivative of the sine function. Okay, so I'm going to leave the 5 to the negative x over 2. I'm going to leave that alone. And I'm going to multiply by the derivative of sine. Remember, derivative of sine is cosine, positive cosine of 2x. And then since it has a 2x, we have to multiply by that, the derivative that we're doing chain rule. So that's times 2. Then add, we're going to keep that sine the same, not touch that. And we're going to do the derivative of the 5 part. All right, so remember we keep, this is the new part, 5 to the negative x over 2. All right, so that's leaving that part alone. Then we multiply by, this is multiplying by the natural log of our base, which is 5. And now we have to multiply by the du, the derivative of the exponent. So that's just going to be negative 1/2. All right, so if you notice that I can factor out that 5 to the negative x over 2 again. And then I'm going to have 2 cosine of 2x minus, I'm going to have that negative, I'm going to put that negative 1 in front of the ln of 5 times sine of 2x. So let's do brackets. Okay. So there we go. Those are some ways that you can see that. Notice that these were combined with other things, so it's not just always going to be a simple derivative. All right, now let's do a log. Let's remember what our logs are. So this is the log of a bunch of stuff. Remember, we can simplify this out, make our derivative process a little bit easier by using our properties of logs. So let's rewrite f of x to be log base 3 of x plus, that's to the 1/2 power. I'm going to bring that in front. So I'm going to have 1/2 log base 3 of x minus 1. And then I'm going to have minus log base 3 of 2. All right, so now we're going to do our derivative. So I'm going to have the derivative of, I'm going to have 1 over u times the ln of our base. Okay, so reminder, if you need a reminder about where that is, you can flip back to your rule number 3, or here, I'll write it here before I get into that. Remember that our derivative of log base a of x is 1 over, remember the x, and then the ln of whatever your base is. Okay, so just a quick reminder. So for this first term, I just have 1 over x times the natural log of 3. All right. And then in the second one, I'm still going to have that 1/2. And then I'm going to have my, let's make it all 1. There we go. Then I'm going to have an ln of 3 in the denominator. And this time I don't just have 1 over x, I have 1 over x minus 1. Okay. And then remember the derivative of x minus 1 is simply 1. So I would have that in the numerator, but that's just the same thing. And then the derivative of log base 3 of 2, that's a constant. So I'm going to be subtracting 0. So let's simplify this a little bit. Notice that I have a natural log of 3 in the denominator in both terms, so I can factor that out. So that leaves me with 1 over x plus 1 over, yeah, let's keep that factored, 2 times x minus 1. And then we can get a common denominator if we want to. So I can multiply this one by 2x minus 1, this one by x. So I'm going to have still that 1 over ln of 3. I would have that 2x minus 2 in the numerator plus x all over 2x times x minus 1. And then I just combine my like terms. So that's 1 over ln of 3, 3x minus 2 all over my common denominator. And that's probably how they'll write something in the book, or the calculator would give you something like that. Right now, let's integrate. Been doing derivatives, let's practice integrating. All right, so we said if we see a to the u, and this is an a to the u with a being 5, our u is, red. Our u is negative 3x, which means our du is negative 3 dx. So I need to multiply that and then divide by the negative 3. So this is going to be the equivalence of negative 1/3 integral of 5u du. Okay, so we said we're going to have a negative 1/3. Remember, we're dividing by that natural log of the base, that natural log of a, so that's going to be natural log of 5. And then I'm still going to have that times 5 to the u. I'm going to go ahead and fill in the x right now because that's pretty easy to do. And you could, since that's a 5 to the negative 3x, you could put that in the denominator, but that's totally fine to leave it like that too. All right, we're getting close to the end. We've got the integral of 2 to the sine x times cosine x. So hopefully you see that u should be our power here. All right, so u is sine of x. Du is equal to cosine of x dx. So we have both the u and the du. So I'm going to have 2 to the u du. And let's practice changing those limits of integration. So if I have sine of pi over 2, think about what that would be, either your unit circle or your graph. Sine of pi over 2 would be equal to 1. And then if I find the other one, sine of negative pi over 2, that would just be negative 1. So these are going to be from negative 1 to positive 1. All right, so now let's do the antiderivative. We know that we're going to be dividing by the natural log of our base, which is 2, and then multiplying by 2 to the u, and we're evaluating from negative 1 to 1. So that's just going to be 1 over ln of 2, 2 to the 1 minus 2 to the negative 1. Okay, so think about that. That's 2 to the first power minus 2 to the first power minus a half. All right, so that's going to be 3 halves. And that's a nice, simple way to write your answer. The only other thing I wanted to show you was our compound interest formulas. All right, so please make sure you have these down. I know you've seen these before. So if we have compound interest and it's compounded n times per year, then our formula is A equals P, remember P is your principal, times 1 plus R over N. N is the number of times per year. R is your rate, that's your percentage rate, and that will be as a decimal, raised to the T power, and that's your time in years. Okay, whereas compounded continuously, that's A equals part. I always remember parts. And then that's your principal, and that's the number E, right? Your natural number E. And then raised to the rate times time. So your interest rate times the time in years. Some of your homework will have some interest in there, and you never know when you might see that again. But it's just more review. It's not really calculus based. It's more of a review of those applications of exponents and logs.